Good morning, good evening, good afternoon, whatever it is in your time zone. I don't have a lot of time, but I'm going to try to do the following. I'm going to make you a summary, and which is going to take most of the time. And by the end of the summary, I will show you the plots. This is based on a work, on an analytical work, which is going to be submitted in about 1 or 2 weeks from now. So most of you, or at least a lot of you, know that for a long time I have been working on stellar dynamics and gravitational waves. Now, I asked myself the question, so in galactic nuclei and globular clusters, the number density and physical density of stars is high enough so that you can expect that from time to time two stars like our suns will collide. Okay, this for one galaxy is not important enough, but what is the event rate for say 100 megaparsecs? This is what I calculated because I was curious about that. But then this was relying on the work of the numerical work of Mark Freitag and Willy Wentz many years ago. They did a set of about 15,000 smooth particle hydrodynamical simulations, and then I realized about something very interesting, and this is what I'm presenting today. So I'm going to look at two different scenarios. The first scenario is such that the stars are colliding at such high relative velocity and a small impact parameter that they are almost a radial face-on collision, and after that collision there is nothing left. Why I was interested in this? Well, I was interested in this because I wanted to look at how energetic that collision could be, and whether this could mimic other things that we are observing in high energy astrophysics. But then the following occurred to me. By looking at the set of simulations of Freitag and Wentz, I realized that there is a threshold velocity below which the cores, because you know that our sun does not have a constant density, the closer and closer and closer that you get to the center, the higher and higher and higher the density gets, right? So at the center of the sun, you have a core with a mass of about 0.34 solar masses, which is much denser than the outer envelope. Now, for a threshold velocity, below that threshold velocity, which was of 2,500 kilometers per second, the two cores form a binary, and they revolve around each other a number of times before they merge with each other. Now, if you are as biased as I am in gravitational waves, because I have been working on this for the last 15 years of my life, you see a quadrupole everywhere. And then I saw a quadrupole. But the question is, how would what detector observe? Because we're talking about masses of 0.34, and a separation of about half a solar radius. And I was wondering what the effect of this gas around the binary would be. Now, the two stars collide. They form a kind of gaseous cloud which is expanding at a velocity which is kind of similar or very close to the relative velocity of the stars that participated in the collision. So it is expanding at about 1,000 kilometers per second. The density is dropping because the thing is expanding with time. But the two cores, as they in spiraling, they drag gas and form a kind of, because they're kind of bondy accreting, and they form a kind of density region around them, which plays a very interesting role. So you are affecting the frequency and more importantly the time derivative of the frequency of that potential gravitational wave source. Therefore, you are affecting the chirp mass of that gravitational wave source. So after doing the calculations, I realized that what Lisa would see, instead of having a small binary of 0.34 and 0.34, because for simplification everything is analytical, I was assuming that two stars have the same mass, Lisa would see a much more massive binary with masses of about 100 solar masses, with a chirp mass that would change over time, so that you would lose the source because you're using vacuum waveforms, right? So that the mismatch is 100% after a short time, to then reappear in the Lisa data stream as a binary with different properties, different masses. You would full track of that binary for a while, and then it would disappear again. And as the orbit shrinks further and further and further, you get to those overdensity regions to see each other, so that the density increases again. And that results into an inflection point in the chirp mass, leading to an increase of the chirp mass going up to masses of 10 to the 6 and 10 to the 7. So that you will see actually something which resembles a binary with a mass of 10 to the 6, 10 to the 7 solar masses. The same applies to the luminosity distance, because the luminosity distance will change over time from rather close distances, because remember that the real distance is set to 100 megaparsecs, but the observed distance would be much larger, going up to distances which do not make sense whatsoever, which would be the smoking gun proof, if not indication, because in physics we don't know have proofs that what you are looking at is not a binary of two supermassive black holes, but two cores of two stars which happen to collide. Now, a much more, even more interesting thing is that when the two stars colliding are red giants, first, the event rates are much higher, because for 90%, about 90% of time of the life of that red giant, the object has a radius of about 25 solar radii. That enhances a lot the event rate because of the cross section. But as you know, a red giant might be envisaged as a self-gravitating polytrope, fully convective polytrope with a degenerate core, which is a kind of white dwarf. Now, I repeated the same exercise. You have these two white dwarfs merging, spiraling, mimicking a completely different source in the Lisa data stream. But the interesting thing is that by the end of the spiraling, they will merge with each other, and they will trigger a very violent electromagnetic event, which resembles a type 1a supernova. And this is a problem. This is a very big problem, because then, if the event rates are so high, it means that this is happening all the time. And if you are registering things which look like type 1a supernova events, but in reality are, white dwarfs colliding with each other, then you run into a snag, because the arguments that based on the cosmic ladder fail. You are measuring distances the wrong way, because you do not have standard candles. The masses will change, and the parameters of the problem in general will not be the same. So, in the last minutes that I have, I will show you the slides, but unfortunately I cannot get too close to the projector, because it's one of these modern projectors and it will interrupt if I just touch or happen to cross the beam. So this is the event rate, and within 100 megaparsecs so it is a sphere of 100 megaparsecs of radius per year as a function of the power law index, because the stars will distribute around the supermassive black hole with a different power law. Now, I'm going to go like this because it's easier. So this is the power law index, and I'm just putting two examples, a 10 to the 6 solar mass black hole, a 10 to the 7. If you look at the values, we're looking at about 100 events per year within 100 megaparsecs in the case of 10 to the 7 solar mass black hole. And this is 10 to the 6, and 10 to the 5 would be around there. So you have at least, I would say, 100 events a year, because you have a full range of values here, right? It's not that in the universe you only have 10 to the 6 and 10 to the 7 solar mass black holes. Now, this is very important. It's important to mention also that I am not considering 10 to the 8 solar mass black holes, because all of this is based on relaxation theory. And if you go to 10 to the 8 and to the 9 solar mass black holes, then the relaxation timescale exceeds the Hubble timescale, and then the analytical argument, the building stone of this derivation just breaks. So this is the energy output, and as you can see, so there is this eta value here, 0.1, 0.3, 0.5 and 1, and this is the only free parameter that I have in my model. It corresponds to the efficiency conversion from kinetic energy into radiation. So the two stars are colliding, sorry about that. The two stars are colliding, you have kinetic energy, and how much of that kinetic energy is going to go into radiation is something that I cannot derive analytically. And I would need numerical simulations to estimate the value of that eta, and I hope this is encouraging for some of you who are doing simulations to look into this problem. But in any case, for some representative values of 10%, 30%, 50% and 100% of conversion, you see that we are in the range of the typical supernova energy outputs. Now, this is the observed, because there are two definitions of temperature here, but anyway, this is the observed temperature of the event in kelvins. You see that the thing cools rather quickly since the event. This is a month for the different 4 different scenarios. I have added 2 zoom-ins here. This is just using Wiener's law. I'm looking at how in electromagnetic radiation, what kind of ranges these events cover, and in principle, but for extremely small time scales, you can see these things in hard X-ray and soft X-ray, but I would expect to see it mostly in near ultraviolet, or even extreme ultraviolet, near infrared, all the way up to very high frequency. I have a much more detailed analysis of this in the paper, but I don't have time to talk about that now. So this is the power output in ergs per second, and look at the numbers, 10 to the 43 up to 10 to the 44 for a 100% conversion, 50%, 30% and 10%. And next to the curves, but not in log scale, because it did not look nice in the plot, I have the typical power law of t to the minus 5/3, which corresponds to a tidal disruption event. So you see that for some weeks these things are going to mimic tidal disruption events. Now, this was what I was talking about before. This is the chirp mass, the observed chirp mass, and you can see that we're ranging from some hundreds of solar masses. So it's changing over time. I think this is strange, right? Because the chirp mass is something which should not change over time. So that this will be identified. This is something like this instantaneous, if you want, observed chirp mass. And this is going to be changing over time. This is the time to merger. Here the merger happens. And you can see that it drops and then it goes up again. This is what I was talking about before. The two cores have around them a region of overdensity that produces this increase in the chip mass by the end of the evolution. And you go up to values of about 10 to the 5, 10 to the 6, 10 to the 7 solar masses. The same happens to the observed luminosity distance. So you go from distances of 10 to the 6 megaparsecs, and again, please remember that we're talking about a source that was set per hand at a distance of 100 megaparsecs. So the two stars are colliding, physically colliding, at a distance of 100 megaparsecs, but they are seen in LISA as two black holes with masses of about a few hundreds at 10 to the 6 megaparsecs, getting closer over time and then going up to ridiculous distances. Look at that, 10 to the 13 megaparsecs when they merge. Now, the case of red giants is more interesting. First of all, the rates are much higher, and I'm talking about orders of magnitude because of the cross section. They are fully convective and non-radiative, and they have a degenerate core that can be envisaged as a white dwarf, right? Now, remember again the argument. When these two white dwarfs in spiral, by the end of the process, they will merge with each other, and they will trigger a very violent electromagnetic event. That event mimics very, very well a type 1a supernova. And then you have a problem. Because the cosmic ladder argument, this standard candle argument, does not apply anymore. We have masses which will vary a lot from one merger to another merger. So that not only the masses, but the properties in general of the collision of the merger will be different. And the properties of the putative supernova will be also very different. Anyway, that was all. This is, as I said, this is in preparation, and is purely analytical. I would be extremely happy if some people would look into this one free parameter that I have doing numerical simulations, and it should be out in archive in, say, 1-2 weeks from now. Thanks a lot.